Good morning, everyone. Thanks for coming along. I'm John Gibbons. I'm Director of the UKCCS Research Centre, and this is the second in our series of seminars on different aspects of carbon capture and storage. We'll be going through quite a lot of topics over the course of the 20 or so seminars, but what we've got today is a very important seminar by Myles Allen from University of Oxford, about why you're doing CCS. It's really fundamental to the whole business of doing CCS. There's not a lot of reasons to do CCS apart from climate change. So it's very important to understand the role of this technology in actually achieving the result we want. One thing I should add is this part of the lecture is being recorded, but when we get to questions and discussion, it won't be recorded. And these sessions are organised only for government employees and our early career researchers. So it's not exactly an open forum, so please feel free to ask anything you like, particularly if you ask it in the chat and it comes up in the discussion afterwards. Nobody else will know what's going on. Okay, Myles, just a quick question to you, just by way of introduction. So when did you start working on climate science, do you think?
Well, climate, 1990 or so, 1989, but I was working on natural variability to start with, and I started working on human influence on climate probably in the mid-90s.
Yeah, and then I think we met talking about carbon capture and storage in the mid-2000s. I can't quite remember when.
Well, that's right. That was sort of not long after we did the work on, well, we realized the sort of limit to the carbon budget, the fact that we only had a finite amount of carbon to dump in the atmosphere, and of course it becomes immediately obvious there's a lot more carbon on the ground than we can afford to dump in the atmosphere, which means you've got to ask the question of what you're going to do with the rest of it.
Yeah, so you've been working on this since about 2000, the CCS link since about 2005 or so. And
that's right, yeah.
15 years on. And
you guys have made a lot of progress. I'm not sure that we have in terms of the policy required to make this happen. Lots of progress on technologies, but we'll get that, I hope.
I'm sorry if I'm jumping ahead, but you did get the IPCC to talk about cumulative emissions.
Oh yes, no, I think on,
that's a really,
and I'll emphasize that in the talk. I mean, we've made a lot of progress on sort of understanding of what we need to do to emissions. Where we've made less progress is people grasping the nettle of what this actually means for stocks of carbon. So everybody agrees that emissions of CO2 have to go to net zero, ideally by around mid-century if we're going to meet the Paris Agreement goals. But there seems to be, people seem to be quite reluctant to accept the obvious corollary of that, which is that we need to work out what's going to happen to fossil carbon after mid-century.
Yes. And just as sort of a personal question, I mean, do you think your technical education, which I guess physicist, was it, that your background? Yeah. Do you think it prepared you for this, or have you had to pick up a lot of new things?
I think so. I think one thing you learn as a physicist is the importance of distilling things down to something as simple as possible, but ideally not too simple, in Einstein's phrase. And that's kind of what I found myself doing over the past 15 years. I spent the first 15 years of my career making things more complicated, if you like, and the second 15 years trying to undo the damage. And I mean, climate change, it's very easy. And you're always hearing, and I find it very frustrating, academics on the radio saying, oh, climate's terribly complicated. It's actually not. I mean, not at the level of what it takes to stop global warming. That turns out to be remarkably simple. And I think we need to get that across to people. And I think that we have made some progress on that, because complexity is very much our enemy in this, because if something's complicated, people can always sort of say, oh, well, somebody else will deal with it. Or you can sort of muddy the waters and carry on with business as usual. So simplicity is what we need. We need clarity, in particular, in the build up to COP26. It is frustrating how, we seem to slip into complexity all too easily. And we were just hearing this morning, from the climate change committees sort of scorecard on the government with a whole litany of things they want to happen, making it sound like achieving net zero in the UK involves a massive shopping list of things that need to change. Lots of things are going to change over the next 30 years, but actually achieving net zero in the UK and indeed anywhere, I'm going to try and convince you, just means one thing only. And we've just got to get to the point of balancing our extraction of fossil fuels with our disposal of the carbon dioxide they generate. And so that means developing technologies for long-term safe permanent disposal of CO2, which at the moment means CCS. It's the only game in town.
Yeah. Okay, well, that's a very good introduction. And I should just also remind people we've got a hard stop at 11 o'clock. And in fact, I'm going to have to leave a few minutes early, but Caris will be carrying questions. Okay, thank you very much. Over to you, Myles, please. We're looking forward to it.
Okay, well, I'll share my screen if I may. Okay, so I've been asked to talk about the science of CCS, the science of climate, and how it applies to CCS. And I'm going to go a bit beyond that brief and really focus on not only the science case for CCS, but the very strong economic case as well, which has been emerging from some recent work I've been doing with Stuart Jenkins, Eli Mitchell-Larsen, and Stuart Hazeldine, and of course many more people as well. I should stress I'm director of the Oxford Net Zero Initiative, which is supporting this work in Oxford. And I'm going to just start off with a few minutes on the science behind CCS, with a few slides inspired by our net zero logo. We designed the logo to tell a bit of a story. And the first part of the story, which, as John was pointing out, is now pretty much universally accepted. It's cumulative carbon dioxide emissions up to the time of net zero that largely determine the warming we end up at. And that was a finding that emerged in the late 2000s. I was involved in a couple of the papers that reported this. There were many others as well. And it was all gathered together in the IPCC fifth assessment report. The sort of crux of the finding is it's the area under that curve of emissions into the atmosphere that matters. And so any delay today in reducing emissions means we just have to reduce faster in the future or take that carbon dioxide back out of the atmosphere again. And that's well illustrated in the IPCC's fifth assessment report, with this figure from the synthesis report in 2014, showing this straight line relationship between cumulative human-induced carbon dioxide emissions into the atmosphere in the horizontal and the warming we get in the vertical. And the reason this matters, of course, is that the total fossil carbon reserves underground would take you, way out here to the right of this slide. So if we want to stop global warming, we're going to make sure that an awful lot of the carbon that we could burn in our fossil fuel reserves is kept out of the atmosphere in some form. Now, I mentioned chatting to John at the beginning, our penchant for making things complicated. A complication that has sort of recently drawn a lot of attention is the fact that our net emissions to the atmosphere are not quite the same as our net production of carbon dioxide from fossil fuel use, because you could, at the moment, we are actually emitting more to the atmosphere than we generate from fossil fuel use, because we're releasing a lot of carbon dioxide from land use change and deforestation as well. But you could complement near-term reductions in the total amount of carbon we generate, which is indicated by the sort of outer envelope of this schematic curve, with storing carbon in the biosphere. And this has drawn a lot of attention over the past few years. The World Economic Forum went very much to town on the idea of planting 1 trillion trees to address the climate problem. But we need to keep the potential, and indeed our government is really pushing nature-based climate solutions as a central element of COP26. I think lots of people like to talk about nature-based climate solutions because there's so many reasons to conserve nature, to conserve forests, to restore ecosystems and so on, that it's kind of a, it makes everybody feel very warm inside, and it's nice and non-controversial. Who wouldn't be in favor of planting trees and restoring our ecosystems? But this does help us. If we drive down emissions in the near term, we can complement those reductions with storing carbon in the biosphere. But this is the really important but, is that it's a long game. Nature-based solutions do have many immediate benefits, but they take a long time to reduce temperatures. Simple reason, trees take time to grow, ecosystems take time to evolve, and so on. So even with our most optimistic estimates of the potential of nature-based climate solutions, they're going to have a limited impact on peak warming if it occurs around mid-century. They might have more impact if we fail to limit warming to 1.5 degrees, and we're talking about sort of more like a 2-degree scenario and temperatures peaking around the end of the century. But we need to recognize that the impact, the maximum impact of storing carbon in the biosphere that we could have is around the sort of 1/10 of a degree level by mid-century. And there's another more profound issue with compensating for fossil fuel use by storing carbon in the biosphere. And this is a figure, a little appreciated figure, but a very, very important one from the IPCC's last assessment report, showing the impact of warming itself on carbon uptake by the oceans and biosphere. So this is the difference between simulations. They're simulations, you have to do this with models, of course. They're simulations with models where temperature was allowed to interact with the carbon cycle, and simulations where it was not. And so the difference in these two tell you the impact of warming itself on uptake of carbon by the biosphere. And really importantly, you can see that around now, this drifts off negative because the warming becomes big enough to actually cause many of the biospheric carbon sinks that we rely on to take up carbon to start re-releasing their carbon back into the atmosphere. And by mid-century, on a pretty middle-of-the-road scenario, this isn't one of the very ambitious, not ambitious, very, this isn't one of the sort of 6-degree scenarios, this is more middle-of-the-range one. But we, even on this scenario, we're seeing warming itself reduce the ability of the biosphere to take up carbon or cause the biosphere to re-release carbon back into the atmosphere at the level of 5 billion tons of CO2 per year. And that, worryingly, is pretty close to the maximum we think the biosphere could take up through nature-based climate solutions. So, it's a slightly subtle message. We want to invest in nature. We need to invest in nature. If we don't invest in nature, we'll actually make those negative feedbacks worse. But because of the risk of those Earth system feedbacks, we can't count on nature as a permanent solution to the ongoing use of fossil fuels. So when Shell invites you to drive carbon neutral by protecting and replanting forests, it's only a temporary solution. You have to recognize that that's not going to last forever. And stopping fossil fuels themselves from causing global warming means scaling up permanent carbon dioxide storage. So this is the sort of main, and that's, by the way, illustrated in our logo by that big wedge of permanent storage. And hopefully somebody on this call will recognize what that's a photograph of. I might leave that in the chat. Maybe say if you think you know what that photograph is of. So this, to emphasize, is the only way to stop fossil fuels themselves from causing global warming. We need, obviously, to burn less by replacing fossil fuels with renewable energy and by using fossil fuels more efficiently. That gets us in the IPCC's scenarios that meet the Paris goal of limiting warming to around 1.5 degrees. That gets us about 2/3 of the way there. but the rest of it is achieved by storing more underground. Now, what I'm plotting you here, this is not the way the IPCC scenarios are normally plotted, but it's the way that I believe they should be plotted. This shows you the total CO2 produced by energy and industry in these scenarios in black, and then net emissions from energy and industry, including BECCS, in blue. And so obviously the wedge between them is the carbon dioxide that in these scenarios we re-inject underground. And you can see by mid-century, it's of the order of a third of our current production of carbon dioxide by energy and industry. This is a huge carbon dioxide disposal industry that somehow these models are relying on developing over the next 30 years in order to stop fossil fuels from causing global warming. But there's a problem, very well illustrated by this figure, actually from a Goldman Sachs report, but it's sort of pretty well supported by similar literature, comparing the cost of different ways of reducing emissions. So this is a very familiar marginal abatement cost curve, and it shows in the horizontal reductions in emissions, going from no reductions on the left to net zero on the right. So this is sort of, this is a snapshot in time, but if you're producing, if we held emissions constant at the current level, which is kind of what you get from current policies, then you'd end up with roughly over 50 billion tons of CO2 equivalent per year being dumped into the atmosphere. So that's your challenge to get rid of it. This shows the cost of lots of different measures to get rid of CO2, and it separates the measures to reduce production, that's the burn less arrow, with measures to increase storage, that's the store more arrow. Now, the important point is that the red line is below the blue line 75% of the way, okay? It's cheaper for 75% of our emissions, it's cheaper to reduce CO2 production than it is to enhance CO2 storage. There are some exceptions, some low-cost afforestation opportunities and so on, but by and large, it's much cheaper to not produce the CO2 in the first place than it is to store it away underground. But then we hit that final 25%. And these are activities which, for which there is no obvious substitute. They're by and large nothing to do with power generation. These are things like aviation, cement production, steel production, and so on, for which either there is no substitute or the substitute is very, very much more expensive than using fossil fuels for that activity. And if we just rely on measures to reduce CO2 production, the red line here, what the Goldman Sachs estimates say tell us is that, you know, even to get to a sort of 80% reduction, we'd need carbon prices of the order of $1,000 per ton of CO2, and then they run out. You know, that they sort of just can't do it. We can't get there with reducing CO2 production alone. We need to start storing CO2 because it doesn't make sense to simply sort of eliminate this last 25% of activities from the world economy when it's far, far cheaper just to store the CO2 that they generate. But this illustrates a fundamental problem that we have, which is until we get to the 2030s or so, 2040s or so, if you're just relying on carbon pricing or an emission trading scheme or whatever, then it'll always seem to be cheaper to reduce emissions by reducing CO2 production than it will be to build up CO2 storage. So we need a different approach. And this is what I'd like to focus on in the last 10 minutes or so of this talk. The idea of a carbon takeback obligation has been around for a while, and it's a way of addressing this problem of knowing that we're going to need to store large amounts of CO2, with at the same time knowing that there's cheaper ways of reducing emissions in the short term. So we've got this temporal externality, as economists like to call it, that we have to contend with, because we need to get investment in that capacity to store CO2 to avoid those eye-watering carbon prices around mid-century. But at the same time, we recognize that there are cheaper ways of reducing emissions in the short term. So the way we suggested back in 2009 addressing this is through a direct regulation. If you're going to dig it up, you've got to start putting it back. And the element of this is that fossil fuel suppliers agree to store a rising fraction, which I'll call S, of the carbon dioxide generated by both their activities and, crucially, their products. S right now, globally, is about 0.1%. For Britain, S is 0, so it starts at 0. And it accelerates smoothly to 100% by the date of net zero. It has to, because that's what net zero means. You can't be generating carbon dioxide from fossil fuel use and not putting carbon dioxide back underground if you want to be consistent with a sustainable net zero world. It doesn't need to be the same CO2 because, crucially, you want a market to develop to discover least cost carbon storage opportunities. So a market in tradable carbon storage certificates, which was Stuart Hazeldene's suggestion, is exactly what we need for this in order to capture low-cost industrial capture opportunities and then allow a progressive transition to higher cost options like direct air capture. Again, one of the things I'm concerned about is a lot of the money that's going into CO2 storage at the moment is going directly to direct air capture. It's not clear we need to do it. What's the point of having pure point sources of CO2 busy venting away into the atmosphere while spending hundreds of dollars per ton on direct air capture today? We will need direct air capture technologies in the future, but right now we should be just capturing CO2 wherever it's cheapest to do so. So this is how it works. The blue lines here are those classic IPCC scenarios driven by a global carbon price. And the gray line here you can see is the sort of current policies scenario, if you like, where emissions don't really decline very much at all. Again, we're plotting energy and industrial process emissions here. We're leaving land use out of this and assuming, therefore, that we do stop deforestation, we do use nature-based climate solutions to compensate for any further emissions from land use. So we're just sort of putting land use change and nature-based solutions on one side and really just focusing on the challenge of energy and industrial process emissions here. So you can see all these scenarios, the energy and industrial process emissions do come down to zero around mid-century or a little bit thereafter in the 1.5 degree scenarios, close towards the end of the century in the 2 degree scenarios. The right-hand panel shows exactly the same scenarios in dark and light blue, but just plotting, instead of the total emissions to the atmosphere, plotting the fraction of carbon that is generated by the use of fossil fuels that is re-injected back underground. So this is that stored fraction S figure. And as you can see, it has to go to 100% because that's what net zero means. So all these curves rise, and they all rise following much the same shape because they have to. If you're currently at 0 and you want to get to 1, there's a sort of simple shape you have to follow by simple geometry. So the red line shows a stylized carbon takeback regime in which you say, right, we're aiming for net zero by 2050. Say you're an ambitious country like the UK with a net zero by 2050 target. What does that mean? 10% by 2030, 50% by 2040, 100% by 2050. It's very difficult to argue with that. I mean, how else are you going to get to 100% by 2050? Depressingly, Norway, as ever, is ahead of the game and looks on their plans that they'll be around 17% by 2030. Good for Norway, but they do have rather specific special circumstances. The UK, despite all the excitement over the new CCS projects in the Northeast, and which are very much to be welcomed, we're going to be at less than 2%, even if we do everything which we're planning to do at the moment. So we've got work to do. The problem, of course, is we're still relying on taxpayer subsidy to make this happen. So it's that 800 million that's being spent on these projects in the Northeast. While very welcome, it's not the way to support this in the long term. There's no way the taxpayer can afford to do this on her own. So frustratingly, we got really close in 2015 to an effective long-term solution to this problem. And this is a line in the energy bill that was proposed in that year by Ron Oxborough, that within 1 year of the Act coming into force, they would at least undertake a consultation on measures requiring, and this was the word that set the lobbyists off in a tizzy, extractors and importers of petroleum to contribute to the development of carbon capture and storage. The idea was dropped after some pretty enthusiastic lobbying against it by Oil and Gas UK and others, but basically it was dropped because of concerns in HMG, in Bayes in particular, or its predecessors, over the potential costs. And this is why I'd really like to emphasize in the last few minutes of this talk some recent work we've been doing actually costing this approach. So first of all, what's the alternative? First of all, any carbon solution is going to be expensive. So the default at the moment is to rely on a global carbon price in effect, or a carbon price that emerges from lots of different regulations or lots of different measures to drive emissions to zero. And if we go back to those scenarios from the IPCC and look at the carbon prices that are needed to get emissions to zero, it's actually pretty consistent. Okay, there's quite a lot of scatter here, but regardless of which social scenario you talk about, these SSPs are different storylines about how the world might develop in the future, whether we're going to be rich or poor or whatever. And then the colors show the climate ambition of our policies in the future, whether we go for a sort of well below, sort of 1.5 degree scenario at one end to a more like a 4 degree scenario at the other. You see that if we, regardless of which social pathway we look at, there's a very consistent or pretty consistent relationship between the carbon price we need in 2050 and the emissions we observe in 2050. And in order to get to net zero, we need a carbon price around $1,000 per ton of CO2. And that's, interestingly, much more than the cost of direct air capture with CCS today. So how is it in these scenarios we end up needing carbon prices that are higher than the cost of capturing CO2 from the atmosphere and re-injecting it back underground in order to get emissions to zero? Well, the simple answer is, and unfortunately, it's almost certainly going to turn out to be true, in these scenarios, there are constraints on how fast you can deploy air capture and disposal technologies. And, there are. So, and we don't deploy them in time. So we're left with no alternative. Rather than capturing CO2 from the atmosphere, we're left with no alternative than to use very high carbon prices to drive out those last CO2 production activities that we need to do to get emissions to net zero. If we took a very different approach and said, no, we're going to regulate carbon dioxide disposal in today, you get a very different story. Suppose we start off with costs of capture and sequestration at the range of $50 per ton of CO2. That's, you'll be hearing more about that in the course of these talks, but that's a reasonable number to use for now. And assume that as we work through different carbon disposal options, this price goes up to $250 per ton of CO2 by the time we get to net zero, because at that point, you might be able to capture some CO2 at point sources, but most of your remaining sources will be distributed, and you'll have to compensate for them by capturing CO2 from the atmosphere. So this is going up more to the cost of direct air capture. So the cost per ton of CO2 embedded in products sold is just this, whatever your fraction has reached, multiplied by the fraction you're requiring carbon, by the fraction that you're requiring companies to dispose of. So, the actual cost to the CO2 user starts off extremely low. And that is shown in the red scenarios here, where we just assume, and this is work we've done recently, embedding a carbon take-back obligation into an emulated integrated assessment model. So we're actually looking at the economic impact of a carbon take-back obligation in a model of the world economy. And what you see is initially, it's extremely cheap, but it still gets you to net zero emissions. But it gets you to net zero emissions by disposing of a very large amount of carbon underground. And because it's so cheap to start with, you end up having relatively little impact on total carbon consumption, on the amount of CO2 produced from burning fossil fuels. So in order to drive that down, it's a good idea to augment your carbon take-back obligation with a demand side measures equivalent to a constant carbon price. So unlike the IPCC scenarios where the carbon price has to escalate exponentially to around $1,000 per ton of CO2 by mid-century, under this scenario, we just start off with what the carbon price needs to be today to get emissions down over the next decade, and then just keep it there. So we're not sort of running the risk of these massive, prohibitive, politically prohibitive carbon prices in the future. The total cost of this is comparable to or less than the cost of cost-effective scenarios relying on a global carbon price. So you'll see that even though we end up storing a very large amount of CO2 underground, it's not that different from what we end up storing in the conventional scenarios, and the overall cost of the policy is below most of these blue lines, which, this is a policy that delivers net zero reliably by mid-century, and the total cost, including the impact on consumption, is lower than the majority of these scenarios that rely on a global carbon price. So just to conclude, we need rapid deployment of geological CO2 storage to meet our climate goals. Nature-based solutions can help, but they don't change this fundamental fact. It's too expensive to rely on direct subsidies on things like contracts for difference or tax breaks. I hope BEIS are listening here. You need an exit strategy from a reliance on contracts of difference. So we need a plan for how we're going to fund CO2 disposal in the long term. The carbon take-back obligation provides that. Regulating importers and extractors of fossil fuels to store a progressively increasing fraction of the CO2 generated by their activities and products provides a reliable and, above all, a predictable path to net zero at an affordable cost. Interestingly, oil and gas companies are now committing to take responsibility of their Scope 3 emissions. This would help them, because suddenly it would level the playing field. Everybody would have to take care of their Scope 3 emissions, and progressive companies would not be being placed at a disadvantage in the market. This would be a dramatic, game-changing gesture for COP26 for the UK to commit to carbon take-back as part of our strategy to delivering net zero by 2050. It's been advocated by the all-party parliamentary group on net zero. It's been advocated by a conservative think tank, so it's got broad cross-party support, but the government is silent on it. And I understand the reason the government is silent is because civil servants in BEIS just don't like it, and I'd love to know why. Thank you.